Hello to all my young friends who are studying in intermediate and they are watching this video. Welcome to Calculus Made Easy series. Till our last video, we discussed the topic of differentiation. In fact, we covered the topic of differentiation. There we discussed what is derivative, how to find a derivative, what are the rules of finding derivative of different kind of functions, what are the methods of finding derivative of some typical functions, derivative of trigonometric functions, inverse trigonometric functions, derivative of algebraic expressions, hyperbolic functions, inverse hyperbolic functions, successive differentiation, and all those things. I hope that you must have seen those videos. If you have not seen them, please do see them before we proceed on this topic. Today we are going to start a new topic, which is application of derivatives, where we are going to discuss the practical application of these things of derivative. So as the name suggests, you can make out that this is going to be quite interesting. So I request all of you to pay a little bit more attention here, and also it's going to be interesting. So let's first of all discuss where these derivative plays a very important or vital role. I'll just depict 2-3 examples. Solving problems such as errors and approximations. We'll be discussing shortly that this is extremely helpful here. Finding equations of tangent and normal at a point on a curve, and finding maxima and minima for a function. Apart from these also, there are many areas where derivative plays a vital role. So we will start with errors and approximations. Before we start discussing errors and approximation, let me just bring to your notice a term which is pronounced as infinitesimal. What do we mean by infinitesimal? In fact, it is used in the sense that anything which is extremely small, very small, that is called infinitesimal. Please note, this is going to be very important once we proceed on this topic. It cannot be distinguished from zero by any means. In so close, see, if you have two objects, say this is A and B. Now since they are easily distinguishable, you can easily make out that this one is A and this one is B. But if they nearly overlap like this, here is A and here is B. So it is very difficult to distinguish which is A and which is B. That means A and B are very close, extremely close, extremely close. So infinitesimal is close to zero, very close. You cannot distinguish between zero and infinitesimal, but it is not zero. This is very important. It is not zero, but it is very close to zero. Now, if we have a variable x, then infinitesimal is denoted by delta x. Just note this notation. We have been using this earlier also. Similarly, for variable y, it is delta y. Now, if we have a function y is equal to fx, then delta y is equal to fx plus delta x minus fx. That we have already discussed earlier, but still I'll discuss it once again. Say y is equal to fx. That means a small change in x plus delta x means a small change in x will produce a small change in y. That means delta y is equal to f x plus delta x minus, you take y on this side, minus y but y is equal to fx, so we write fx. That's how we write this expression. Hope I am clear with this. Now let's start the topic. Say you have a function y is equal to fx. On this curve, we have a point A and the coordinates of A are x and y. That means this is x and this is y. We make a small change in x, which is called delta x, and we get a point on curve which is say B. Now when we have made a small change in delta x, we will get a small change in y also, which is delta y. It can be positive, and it can be negative also. Suppose the curve has been like this, then if this is x and you make a change of delta x here, so you will get delta y as negative here. So it can be either way. So the coordinates of B are x plus delta x, y plus delta y, or we can also write x plus delta x, fx plus delta x, because y is equal to fx. If x, this is x plus delta x, so y is equal to fx plus delta x. Instead of y plus delta y, you can write x plus delta x also. We just join A and B with this purple line. Say this point is C. Now we draw a tangent at A. We draw a tangent at A and let it cut this line BC at point D. Say this is dx. We name it as dx. As you can see, delta x is equal to dx. And dc is delta y. I hope I am clear. So we can clearly make out that although delta x and dx are equal, but delta y and dy need not be equal. They may not be equal, because if this is a curve, instead of this black curve, if it were a straight line like this red, then dx and dy will be equal. Say for example, this y is equal to fx becomes a straight line like this, which overlaps with this red line. Then only delta y and dy will be equal. Otherwise, there will always be a difference. You can see here delta y seems bigger than dy. I hope I am clear with this. Now, if delta x is infinitesimal, what we discuss right now, that delta x is extremely small, what will happen? Just see, I am going to depict it with a few slides. Let us decrease delta x. Now here you can see this is delta y and this is dy and this is delta y. So there is a big difference. Suppose you break it closer. What happens? The difference has reduced. The difference starts reducing. And at this stage, when delta x is infinitesimal, delta y upon delta x will be nearly equal to dy upon dx. This is the sign nearly equal to, and this is the sign which you use for equal to. So you must be aware of these terminologies and notations. So when delta x is infinitesimal, this delta y and dy are nearly equal. So instead of delta y upon delta x, we can write dy upon dx, right? Because they are nearly equal. So we use this notation. Now what is dy upon dx? And please note here, I can't make this delta x very small in depiction because we have our own limitation in drawing, otherwise you will not be able to see. That is why I have just demonstrated by reducing delta x a bit, and you would have uh, observed that delta y and dy are coming close to each other as delta x becomes smaller and smaller. You can appreciate this. Now what is dy upon dx? Dy upon dx is the slope of a red line that is tangent at A. Red line is tangent at A. Now we already told that the slope of tangent at any point on the curve is the derivative. That means dy upon dx is equal to derivative of function at A. So we can write like this. Hope I am clear. So delta y upon delta x is nearly equal to derivative of the function at A. That means since delta y upon delta x is approximately equal to f dash x, it is not equal to. Still, there may be a small quantity which may be added in f dash x so that it becomes delta y upon delta x. So we are telling there exists again one more infinitesimal epsilon, which we are denoting by epsilon, such that delta y upon delta x is equal to, if we replace nearly equal to with equal to, so it will be f dash x plus that epsilon. There will be a very small difference. That means delta y is equal to f dash x into delta x plus epsilon into delta x. Hope I am clear. So we write the equation like this: delta y is equal to f dash x into delta x plus epsilon into delta x. Now since epsilon is infinitesimal and delta x is also infinitesimal, so they both are extremely small, so their product is even smaller. So we can neglect this term. That means delta y can be taken as approximate value of f dash x delta x. Hope I am clear with this. So approximate value of delta y is f dash x delta x. So f dash x delta x or dy is the approximate value of delta y. Why we are writing dy? Because we told you that dy is the approximate value of delta y. See, dy upon dx is equal to f dash x. Now dy is equal to f dash x into dx. Now dx and delta x are equal. So dy is equal to this, and dy is approximately equal to delta y. So the approximate value of delta y can be written as f dash x delta x or dy. So whenever they write dy, so you can understand, you can make out that it is approximate value of delta y, or it is expressed as f dash x delta x. So f dash x delta x is the approximate value of delta y. So how we write that? This is our first expression. Delta y is approximate value of f dash x delta x. First equation. Now what is the actual value of delta y? Now we told that f x plus delta x is equal to y plus delta y when y is equal to fx. That means delta y is equal to f x plus delta x minus y. Y is equal to fx. This is the actual value of delta y. This is the actual value of delta y. So we can write it like this. So now you have two equations. One is the actual value of delta y, which is given by equation number 2, and one is approximate value of delta y, which is given by equation number 1. From 1 and 2, we can write that f x plus delta x minus fx is nearly equal to f dash x delta x. That means f x plus delta x is nearly equal to f dash x delta x plus fx. This is the our third equation. Hope I am clear with all these three equations. So these are the three equations, and in fact the first two are the main equation. The three is the derived one from 1 and 2. But you should remember in this chapter these three equations. Delta y is approximately equal to this. Delta y is actually equal to this. And fx plus delta x is approximately equal to this one. Right? Now, if I ask the actual value of fx plus delta x, the actual value of fx plus delta x will be fx plus delta y. This will be actual value of, because we just said y plus delta y is equal to f x plus delta x. So actual value of delta x, fx plus delta x is, now y is equal to fx plus delta y. Actual value of delta y. This is actual value. So from these equations, we find approximate and actual value of delta y or fx plus delta x, which will be more clear once we start doing problems. So what do we mean by approximate and actual value? Let me explain by an example. Take the example pi. You all know what is pi. Now, the actual value of pi is 3.1459, and it goes till infinity because it's an irrational number. But we take 22 upon 7 as the approximate value of pi, which is equal to 3.1428 and something. So this is a approximate value, and this is actual value, which is an irrational number, and it goes to infinity. So Let me give you another example. If a number A is very close to B, then A is called the approximate value. For example, 2.718 is the approximate value of Euler number E. Euler number again is a irrational number. Its actual value is like this, that digits go till infinity. But for all practical purposes, this is taken as approximate value of E. So let's again take a quick recap of our learnings, what we have learned. If there is a function y is equal to fx, if there is a small change in x, that is x plus delta x, this will result in a small change in y, that is y will become y plus delta y, and y plus delta y will be fx plus delta x. So exact value of delta y will be fx plus delta x minus fx. Exact value of fx plus delta x will be this, and approximate value of delta y will be f dash x into delta x, and approximate value of the function, that is fx plus delta x, will be y plus f dash x delta x, or fx plus this one. I hope I am now clear with this. Let me again give you one example which will give you more clarity on subject. Say we have to calculate volume of a cube of side x. Now volume will be function of x, which is equal to x cube, right? Now if I make a small change in x, what will happen? This will become x plus delta x whole cube, and my volume is going to be increased by an element of delta y. Now this is the actual increase in volume, which is called delta v. Delta v will be equal to x plus delta x whole cube minus v. V is x cube. But instead of doing all these calculation, I just wanted to know what is the approximate increase in volume which I am getting. So I will find approximate value of delta v, which is dv, which is equal to f dash x delta x. Now f dash x I will get from here. F dash x is equal to 3x square. So here we will get 3x square into delta x, right? So delta x may be the increment also, or it may be the error also. Suppose you make a very small error while measuring x, so this will result in a your small error in v, which is delta v. So you can find the accurate value or the approximate value like this. I hope that you got an idea, which will be more clear once we start doing the problems. Now if Ke is the exact value of a certain entity, say length of a side, square root of a number, and so on and so on, and Ka is the approximate value. Now actual value is, for example, if you are measuring a length of certain thing and actual length is 3.15786, this is the actual. Your approximate value you calculated as 3.1578. So what is your error? Error is A minus E, which is equal to 0.0006. That